plus medyo adiabatic non-isothermal tayo. So in the textbook of Hagler, there's a summary actually of the different equations for uh, okay, different equations for adiabatic and non-adiabatic for different reactors. Okay, so what we have seen the last time, okay, is the general energy equation that you will be using to derive all those equations that you will need for a non-isothermal reactor. Okay. Thermochemistry for the non-isothermal reactor design again. So we have here for the reactor design, we have to start again with the mole balance. So your mole balance, this one is for a plug flow reactor. And you have the rate law, okay, and the stoichiometry as well. So for CSTR with the heat exchanger, the heat transfer rate is UA, the overall heat transfer coefficient. A will be the cross-section, the lateral surface area plus the top and bottom area of your reactor, the total surface area, and then the difference between the fluid temperature T sub A flowing in and out of the batch, in this case, STR, pala, sorry, minus T, the temperature inside the reactor, which is changing. Okay, so the heat flow to the reactor is in terms of overall heat transfer coefficient, okay, Q, UA delta T. So that's delta T, the difference between the temperature inside the reactor that is variable, changing with X, okay? So just imagine this is changing with X, this Tx, and TA will be the fluid temperature. So this TA could be constant, or the entrance and an outlet will be different for the CSTR. Okay. Then, so review terms in the energy balance again, going back to our derivation. All right, so we have again summarized now our general energy balance. Okay. Okay, so for the steady state operation, all right, this whole energy balance, the energy of the surrounding that's affecting the system, energy of the surrounding, which is Q and work, plus the energy of the system, which is this. All right, so we can simply simplify this into enthalpy of the reaction and the enthalpy of the incoming reactants, okay? As they are entering the reactor at a certain temperature T sub IO, all right, to final temperature of the reactor. So this will be the energy of the reactants entering, okay? As the temperature of the reactant changes from Ti sub O as they enter, okay, Ti sub O to the temperature inside the reactor. So this is the delta T. Now, if there is phase change, of course, the final equation for the material, for the energy balance will be this. Okay, if there is no phase change, this enthalpy can be expressed in terms of Cp. All right, so you see the overall enthalpy for the reaction at temperature T. So this is system, so surrounding, and this is the energy of the system. The reactant entering the reactor, changing its temperature or phase, and this is the enthalpy of the reaction, heat of the reaction. So this involves the reactant entering, since there's no product entering. So the two possible heat that will be involved here is the change of temperature of the reactants at TIO to T of the reaction or reactor, and the heat involved for phase change. Okay, so if there is phase change, usually the form of the energy balance will be in the form of enthalpy here. All right, so okay. Now, if there is no phase change, the enthalpy for that term, for this term, will be defined in terms of heat capacity now. All right. So, andito yung discussion na yun. So, for the tubular reactor pack bed, so if there is a heat exchange, so there will be a Q in the form of the integral of U from Ta minus T, integrate that from initial area to a final area, superficial area. But then, of course, the total area and volume of the reactor will be defined in terms of A. Okay. So the heat transfer to the perfectly mixed PFR in a jacketed PFR will be this, wherein pH is assumed to be constant. All right. Or it can be variable based on the inlet and outlet. So for a jacketed PBR, perfectly mixed in jacket, so this is now the energy balance, the heat transfer. Okay. This will be the heat transfer for the Q. All right. So the Q will be equal to the right overall heat transfer coefficient times the area, heat exchange area per unit volume, this A, and then delta T over the density of the bulk fluid. Okay. So that will be the formula for our Q for a plug flow reactor. So again, so for the non-isothermal reactor design, going back to our overall energy balance. Okay, so if we're talking of adiabatic, okay, later you will see. So this is the steady state operation, zero accumulation, QWS, and then of course the transition from you combine your enthalpy entering and leaving for the, in this case, this is the reactants. Okay. And so this HI refers to that of the reactant leaving the reactor. And so you have here at a particular temperature, all right? So you have here the no phase change, all right? We can express this H in terms of your standard enthalpy again, plus that of the heat capacity by the transition from, again, the temperature of the reaction to some reference temperature, because you cannot measure directly the enthalpy of an individual species at a certain temperature T. Follow, class? That's why you have to divert the direction, the path of your process so that you can measure this delta H. All right, this delta H that you want. So you need to go through, you bring down the temperature again, and then have the reaction here and have the product go back to the original temperature of the reaction. So this is the initial and the final state are still the same. So enthalpy, since it's a state function, will have the same value as the enthalpy summation from 1, 2, 3 steps. So this is equivalent to the Q, where in Q1, Q2 is the sum of the enthalpy of the reaction. Same lang yan. Q of the reaction for each step. So since Q is additive, so the sum of Q1, Q2, Q3 must be equal to delta H. You know already this path, right, class? So I always interpret this in terms of, okay, so that you can see better mathematically how we define that. So basically, delta H1 is H2 minus H1, right? And Q2 is simply H3.3 minus H2. All right. So this is one. And for Q3, this Q3 here, that's say point 0.4 H4, the final destination minus H3. And so take the sum. H2 will cancel, H3 will cancel. So that's why enthalpy, we say the sum of these three Qs are the same as the final, which is H4 minus H1, the initial. That's why I call it a state function, dependent only on the final and initial state of the system. Follow? That's why you define that enthalpy this way most of the time for enthalpy of the reaction or any individual species undergoing change in temperature. All right, so that is how we define enthalpy. So for no phase change, that enthalpy is defined in terms of heat capacity and standard enthalpy. So these are the detailed calculation. And so if we are going to define now the Q minus WS, again, FAO in terms of CP, delta H of the reaction. So you will get to define this. Okay, so this H here and H here will cancel. All right, so what remains is this and that. And so we can cancel the T sub R again of that when we take the sum of both. So you get to define this overall. So basically, we end up defining the simple definition again of enthalpy from initial concentration, temperature of the reactant to the final temperature of the reactant inside the reactor as soon as they enter the reactor, which is a variable T. Okay, so dt. All right, so that will be your integral of heat. So next, let's proceed to the next slide. So going back to that constant average heat capacities, so we have this final overall energy balance. Okay, so from this overall energy balance again, class, we are now looking at the relationship of T and XA. Okay, so from there you derive TX relationship. Okay, so let's derive na the TX relationship from energy balance using this equation here. Sorry. All right. So enthalpy of the reaction again is defined in terms of the standard enthalpy plus that of the delta Cp of the reaction. So knowing your enthalpy again, enthalpy of the reaction, again, the same path as what we have identified earlier, that enthalpy of the reaction based on standard and delta CPT. And delta Cp again is delta Cp product minus reactant. So this is just a review of your enthalpy calculations for a reaction. And so considering a constant average heat capacity, so you have here your overall energy balance. Defining enthalpy of the reaction using the standard enthalpy reaction and delta Cp. And this is now our final working equation here. So you can see from here that this is T and that's T, and then you want to know XA. Now this is actually complicated then. So initial feed temperature is TIO. So again, if this is a solution, you have all the components or the reactants in one solution. So this is just T sub O if you have the solution. So T reference point is this. Okay, so simplifying further that energy equation, all right, so simplify muna natin ulit. So you have here the energy balance for conversion. Okay, so rearrange to isolate terms with XA on one side of the equation, so we get to define XA in terms of T. So the temperature is found on the upper and lower part of the equation, the fractional equation. But then again, simplifying further to make the solution easy. All right. Now for adiabatic, therefore, you have to say Q is 0. So adiabatic, no heat will leave the reactor. It will just be inside the reactor. So what happens to temperature is that the temperature continuously increase. If it's exothermic reaction, so what will happen to the conversion class? You study chemical equilibria, right? As you increase the temperature inside or increasing the heat accumulation, the conversion is much lower. All right, so you can see that based on the example problem that we will illustrate later. Okay, all right. So I will not ask you to derive the whole energy balance. Meron naman yan sa book. Dinerive na sa book. So rearrange again, setting the for adiabatic reaction. Again, which term of this equation is zero for solving adiabatic, right? That's Q. Okay. When the reaction is adiabatic, therefore, do it again. Show the adiabatic operation. So X will be this. Okay, zero yung X for the adiabatic operation. So this will be the same for all types of reactors, whether it's batch, semi-batch, or plug flow, or CSTR, or packed bed. This is the same formula for all types of reactor. Because the Q term is different for each type of the reactor, the rest will be the same. So if there's no Q, then this will be the same for all. All right, so simplify, dropping your FFA. And so this will now be your final simplified form. Okay, so this is going to be used for the material balance so that you can solve the design equation. Okay, so of course, most of the time, this delta CP term here will cancel. It will be negligible for most cases. So that the final equation will be simpler in terms of TX relationship. Okay. So you have this again, constant or mean heat capacities. Okay, shaft work is zero. Further simplify that. If there's no shaft work, then therefore you can have this simple relationship of X and temperature. So with this, you can see that the X and temperature are linear for Q and S, zero. Okay, so same for all process. So if the case is that the value of delta CP is much less than this value, so we can neglect that, we can drop that. And so you can see that X is linearly dependent on T. Okay, so that linear relationship is seen here. X increases as T increases. So that will be the same for all types of reactor. Okay, questions of our class? So this will be for the adiabatic, no? And so non-isothermal CSTR adiabatic. So let's have one example. Okay. So solving that again. Pakita uli natin again and again our equation. This is our working equation. So from the design equation for a CSTR for the material balance, this is what we get. All right, we obtain the volume expression in terms of FAOX times R, negative RA. So it's simply the, when we did the, in your kinetics one, when you do the, what you call that, graphical integration. So this is somewhat your Y, and this is somewhat your X. So later you will see this. So energy balance again, adiabatic, this is almost negligible, always negligible. So this is what happened. And if this is also negligible, so that will simplify further your equation. Okay, so you know what to do now, how to rearrange that equation. Okay, so the rate law, all right, the design equation coupled with the energy balance equation will complete your solution. All right. So again, if there is no Q, this will be the left side will be 0. Okay. So rearranging this based on the definition here of with Q. Okay. So no shop work, but there is a Q involved. So this is the amount of heat that must be absorbed by the cooling system. And this is actually the heat involved for the reaction plus the heat involved to change the temperature of your reactant from TiO to T. Okay, so summing up, so this will somewhat be grouped into this equation. So you can rearrange. So Cp delta T. So this is somewhat mCp delta T. So that will be the total Q gained by your reactant. So in this case, this is the heat that is being removed, and this is the heat of the reaction. All right. Heat being removed, heat of the reaction. So somewhat heat removal, and this is heat generation term, and equal to the amount of heat that is gained by the uh, reactant. So in the incoming in the reactor. So from TiO to T. So this is how much the internal somewhat. Okay. So the gain in energy of your reactants will depend on this difference between the absorption or the heat that is being transferred, all right, and the heat of the surrounding and heat of the reaction itself. Okay. This is my lecture 2. So there are two types of calculations involved for CSTR, wherein you are going to solve for T at the exit temperature inside the reactor. So this is the temperature inside the reactor, the final. Okay. And then you calculate therefore for the K, which is a function of temperature, where T is calculated in step A. All right. And plug the K calculated based on the T calculated into step B. All right. So that you can have the design equation to calculate for the volume of your CSTR. So this is the given flow rate. You want to know the temperature and volume. So given XA, so you can simply solve directly the temperature and volume of the CSTR reactor. So this is direct calculation, just having one unknown. Okay. So given that. So there's another type of problem involved for a CSTR, case 2, wherein you're asked to find the composition and the temperature given the volume. So in this case, this is going to be somewhat solve for TV as a function of XA. All right. So this is requiring the TX relationship. And so solve for the CSTR design equation for XA as a function of T, and then plug that in the K expression. So TX relationship, substitute here. So you only have one unknown, which is X or T. So plot your conversion versus T and the conversion using energy balance and conversion using material balance versus the temperature on the same graph. So this is somewhat uh, graphical. You can do graphical, you can do analytical. So this requires some Actually, it requires some numerical technique if you want for the analytical solution for the numerical technique. So the intersection of these two lines is the condition of T and Xa that satisfies the energy and mass balance. So graphical. So since the final conversion, whether you use the energy balance or material balance, will be the same. So the intersection of the two will give you the temperature, final temperature, as a function of XA, the final XA. Okay. All right. So we'll give you that type of conversion determined from the energy equation. So you have to define conversion from energy balance, or you can also define conversion final at equilibrium using material balance. So since the conversion for both energy balance and material balance must be the same at the exit point of the reactor, so that will give you also the exit temperature, the temperature at the end of the reaction. Okay, so those are the two types of applications in CSTR. So for application to a steady state PFR, so we have negligible shaft work, adiabatic condition. So again, we have the use of TEB to construct the table for T. And again, you have to know your temperature as a function of X using energy balance. And therefore, if you know T already as a function of X, you can measure K as a function of X as well. So you use stoichiometry to uh, define RA and then use RA now in your equation to measure this volume. Okay, now this is a PFR. So it has to be a differential equation. Okay, let's apply now our equation. So that's the two equations for adiabatic PFR. This one is adiabatic PFR. This one too is adiabatic PFR. So we have this two cases. Okay, so these are the simplest case for our topic in non-isothermal, the adiabatic case for both CSTR and PFR. Are we ready now? So let's start our simple problem here. All right, 523. So first order reaction A and B. Okay, class, are we ready? If you have questions, let me know about your energy balance. Again, this is the overall energy balance. So if you, as much as possible, you want to show this energy balance and then proceed with, if it's very simple to get the TX relationship, especially for adiabatic, no? So you can start with this working equation in your problem set or exam and show us how you obtain the TX relationship. So in this case, for reaction carried out adiabatically in a CSTR. So we are given this case wherein A is known, these are known. You want to find the reactor volume that produces a conversion X sub A. So here you want to know volume and conversion. So you know already your temperature really based on the TX relationship. So we define our TX relationship. If T is unknown, X is unknown. Okay. So the heat capacities of A and B are known and they are equal and shaft work is negligible. So the energy balance when it comes to thermal energy balance, therefore for T will be this. Okay. So again, you have the Q of the system, the surrounding, Q component of the surrounding, and this is the system, the feed entering, and then this is the reaction. Question about this three group of conversion, and also this is the conversion, how much is used up. So that will determine the quantity of heat that will be produced by the reaction. So this is the Q of the reaction actual. And this term will be no phase change, so that you will only have to measure how much is the heat absorbed or given off by the reactant as it enters the reactor. So this is the second term. And of course, this is the net heat uh, supplied by the surrounding. Okay, Q minus WS, sorry. Okay, questions so far, class, in this discussion? So those are the important part of this energy balance so that you need to define. So sometimes you really have to define, be able to define your working equation so that you can understand better your problem, how to solve the problem. Okay, so we're talking of adiabatic, no shop work. And so we have this final equation. And so we can simplify further left and right. Okay. Okay, na-cover kasi yung 2. Okay, alisin natin. Left and right so we can see the simplification now. Simplify as much as possible your working equation and then obtain the value of XA, multiply out the XA, and isolate your T. And so with that, factoring out the T. And so this is the final, okay, equation that you can find from your textbook. Okay, class. So what we need to present in our work is the, since we have studied already how we derive, so you just have to show this first equation and maybe the final equation here. Okay, so in your work, you can just simply show this. If the solution is very long, but sometimes solution is very short naman because you can simply drop this term na. So you don't really have to go through this laborious derivation. So, but then again, okay, you can find this also in the textbook, this adiabatic, okay, equation here found in the textbook. Okay, so with that, so you have your x as a function of t, or t as a function of x in this expression. You can just see the final equation in textbook. All right, if you're dealing with, okay, temperature when XA is specified. So if you know already your XA, you can simply measure temperature. And so plug in the values of delta Cp, delta H, your temperature, so you can compute them directly given in the problem. Okay, so that's very direct. In terms of CSTR, most calculations are very direct. So no need to do differential equation solution, but simple F solve will be enough. Okay, so that is for the adiabatic CSTR. Okay, so this is our working equation again. Any question about this equation, class? So this is the final TX relationship from energy balance for CSTR adiabatic. So calculate now your K because you already have your X. This is known, that is known. Everything is known, all right? So calculate your T based on given X. All right, so in that case, we have, all right, so we can calculate na as well the K value and plug the K value in the rate law expression when the specified XA is reached into the design equation to calculate for your volume based on this. So once your K is calculated, substitute in RA, and so you can define volume of the reactor. Okay, so that's how simple this calculation is for a CSTR. Okay, so since you have this T now, I can plug that here. And then once I know K, I can measure my RA. And so I can measure my volume now. All right, so you have that. Okay, so let's apply our equation now to a problem. So these are the steps. And what are the example problem that we have? So again, you can further simplify your working equation. So you end up with volume as a function of X and volumetric flow rate and that of K. As simple as the definition of your tau, residence time. Definition of residence time in terms of conversion is simply this, which you already derived before. Yes, class, you derived that before, na? The tau expression in terms of conversion. Correct, class? Residence time.
Yes, ma'am.
Okay, diba? Recall that. So this is a simple problem. Then next week, medyo complicated na. So we have an example here of an adiabatic with a given value of CPA 300 Kelvin, the inlet temperature of the reactants, and the heat of the reaction is known, so you don't have to calculate them. This is already the heat of the reaction, the delta H R standard plus delta CP. So this is already known. This is heat of the reaction, which is the whole of that. Okay. And so you only have this and that. And therefore, since based on this problem, okay, very direct itong CSTR. This is adiabatic, WS is 0, FAO therefore can be simplified. And so enthalpy of the reaction is known. And you just have to find the value of your summation of pi CP. Again, the summation of pi CP is simply, of course, everybody knows how to measure that. For component 1, if there is A, so um, so pi A is simply FAO over FAO, so that is simply 1. So pi B, therefore, is FAB O, initial flow rate of B, over the initial flow rate of A. So that is just your value of pi. Okay, so this is your FAO over FBO over FAO, the ratio with respect to the flow rate of your limiting reactant A. So in that case, we have this summation. This is 1 for A and CP of A. Okay, and then so therefore you have for CP of A, which is 50 calorie per mole. Okay, and then that is also, A lang pala, sorry. A lang ang ating reactant, so there's only one, which is 1 pi. Okay, so since you already know that pi, T minus T sub O, again, unknown pa yung T, TO is known, which is 300 Kelvin. Delta H reaction is known. So this is very simple one. So everything is given na. So finding therefore your TX relationship will just be this one. All right, so XEB is the X conversion that you obtain from defining your energy balance. That's why it's labeled as conversion obtained from energy balance for a CSTR. As you can see from energy balance, the relationship of X and T is linear. And from material balance, which we have in the previous slide, okay, this is material balance. No? So this is from material balance wherein the volume X and RA is non-linear. So it's not a linear relationship between your V and X. And that will be, therefore, if the X from material balance and X from the energy balance is plotted against each other, then the intersection of these two will just simply give us the X at equilibrium and T at equilibrium. Okay, so that, okay. So graphically, we can combine, or you can just equate that X for energy balance and material balance must be the same. So you can solve for T. All right, so solving for T, Now we have in this second example, okay. So that is the first example for number one. Sorry for that. All right, so that will be your XVT. Okay, so this is our answer. No? Just have to plot this. You can plot using your MATLAB again. You practice class. You can use this same problem and then compute 40, obtain, because XEB and XA are equal. All right, they are just the same at equilibrium. And so you're also solving for the same T here, whether it's energy balance or mass balance. Follow, class?
Yes po.
Okay, so these are the intersections. So mostly graphical or you can do analytical as well. Equate na lang pag analytical. Now, this is another example, irreversible elementary liquid phase. So you have 2A forming B carried out adiabatically in a flow reactor. This time it's a plug flow reactor without pressure drop that the feed contains equal molar quantities of A and an inert liquid. So there's an inert liquid here. All right, so your feed is A plus an inert material. And then your final product is B. Okay. It's adiabatic again. So meaning to say the heat is maintained inside the reactor. Walang lumalabas na heat. So you can compare that when you have your homework. Adiabatic muna isa-solve nyo. Then later, yung susunod na assignment, if you consider the reactor non-adiabatic, compare the previous solution or answer. Okay. And so the feed contains equal amount of A and inert. So same lang. Same. The feed enters the reactor at 294. Again, you're always given the initial temperature of the feed, which is 294, and initial flow rate known, and then concentration of A is also known. So these are the given concentration. From the concentration and volumetric flow rate, of course, you can find the volume molar flow rate of A. All right, so you know how to do that. So the feed enters the reactor with 5 bm cube as the volumetric flow rate, concentration of 1 mole per dm cube. What would be the temperature inside the steady state CSDR that achieved 80% conversion? So you want to know the temperature inside at 80 degrees, at 80, sorry, 80% conversion. Should be very high. So extra info will be this. Okay, these are given. So given this data, you can now start solving that energy balance and material balance to work on that final temperature inside the CSTR. So as you can see, class, the heat is accumulated inside. So it must be a very, very high temperature. All right, so let's start with the energy balance, steady state. All right, solving for T. Again, we always try to write the original energy balance equation, the final that we derive, and then try to simplify again. So you have to get used to this at the start. So you might as well have this practice na lang. Okay, class? Kung hindi naman ganun kahirap mag-derive, isulat nyo na lang. Kaya? Or copy-paste. At least you know what are the equations involved in your equations. Okay, again, this is the temperature X relationship. And so again, identifying the component of this equation. Let's start with delta Cp for the reference temperature at XA. So delta Cp again. Delta Cp is simply product, which is B over A, for example, B over A, the the normalized form of the equation is P over A. Delta Cp product minus reactant based on the limiting reactant, which is 1 mole of A. And so if we're talking of 1 mole of A, the delta Cp of A, the Cp of A is 15. CPA minus CP product minus CP reactant. Okay, then, all right. Of course, the heat capacity is always a function of per mole. It's an intensive property, okay? But you want to define the extensive property, so you have to multiply by the mole based on balance equation, okay? So if delta Cp for product minus reactants are equal to 0, which is most of the time equal to 0, therefore, the value of the summation, all right, for in this case, delta Cp will be 0. And for the other one, the pi Cp summation will just be equal to, for A, pi of A is simply 1 plus that of the pi of B, okay, simply 1, CPI. And so what is the incoming species? So the incoming species belongs to A, and that belongs to inert, equal number of moles. So equal number of moles. So flow rate of A and that of inert will be the same. So flow rate of A initial over initial flow rate A, flow rate of I initial same as that of A. So both are equal to 1, the pi of A, O, and this is pi of inerts. All right, question class. And so heat capacity for both are the same. So this is the summation of pi Cp. So you get this to be equal to 0. This is okay. And this is also 0 now. And so you know this already. And all right. Of course, this will not cancel with that because that is separated by plus sign. Okay, don't forget. That is plus sign. So you cannot cancel these two. All right. So follow class. Question. So you were now able to identify the parts of your equation. So you're now ready to solve for Tx relationship. Substitute all those values and see the calculations of Tx. Simplify your Tx therefore. Again, enthalpy standard pa rin. And if you have the Cp of each product and reactant, so you can perform the uh, enthalpy reaction standard because you have the Cp enthalpy for product and reactant. So you calculate the enthalpy of the reaction, which is negative 5,000. So anyway, so with all those calculations, you have now the constants that you need to put in your final equation. And so that gives you the relationship of Tx. So t as a function of x, but for a CSTR, again, you always have to identify in this problem, the x sub a final is already defined. So the temperature inside the reactor at 80% conversion of A in a CSTR is 427 Kelvin. So that's around 200 degrees Celsius. So it's very high. All right, so just imagine that in order for you to obtain an 80% conversion adiabatic CSTR, you need a very high temperature, which is not practical for an operation in a reactor. All right, so you may want to lower that temperature soon when we go to non-adiabatic. So this is the non-elementary reversible reaction. So you have here your, once you have the value of X, A, and T at 80%, okay, the temperature is known. So from the stoichiometry, you can measure na your K. And then you have your CA as well defined in terms of X. K is calculated as a function of T. All right. So you can evaluate K at the temperature of the reaction for 27. And so once you have your K, you're now ready to put that K in the volume design of the reactor, CSTR. All right. So given everything, you can measure the volume of the CSTR to be 370.9 decimeter cube. All right. So that will be your volume for the reactor. For a CSTR, 370. This is irreversible, na? Elementary. What about the previous one? Liquid phase, no? Oops. Okay. Will this be the same? Ay, sorry. CSTR. CSTR pa rin pala tayo, class. So, sorry for that. So, again, go over that equation and so we can substitute directly the values of temperature and then X. So, for the volume, by evaluating your K first, so you can measure your rate law. So 370. Okay. Then irreversible carried out adiabatically. Okay. The feed contains equimolar paren. The feed enters the reactor at at the 294 and volumetric flow rate of 5 and CaO of 1. Okay, in this case you have, do we have the same case? 294 Kelvin in entrance of the feed. Is that the same as the CSTR? 294 then class CSTR. And now we're doing a solution using a PFR. All right. So this is a 2-point rule. Same conditions. But then you just have to make the reactor CSTR to PFR. From CSTR to PFR. Okay. Okay. All right. Any questions so far with the CSTR calculation, class? Okay.
No.
Okay, no. Okay, very good. So this one is that we have a PFR reactor. Same, exactly the same condition. So what if we have a PFR? This is liquid phase, no? So use the energy balance again to calculate the table as a table of T as a function of X. And then we have the TX relationship already defined. Whether it's a PFR or a CSTR, this relationship, this TX relationship plus this one. Oh, okay. This one. This is the TX relationship. So 166 times X plus 294. That's the TX relationship. All right, so we get to define the TX relationship for a CSTR and PFR, just the same. And so we are now working with the PFR reactor. So in that case, since T is X, T is dependent on X. So 2-point rule lang, just to show the simple relationship of the parameters involved in this design equation. Mamaya na yung maraming XA, delta X. So let's just have a 2-point relationship, 2-point rule from initial to final X. So yan, 2-point rule lang. Just to demonstrate the application in a PFR. So if T is 0, I mean, if XA is 0, definitely the temperature will be the initial temperature. And if conversion is 80%, the temperature final as calculated will be 427, the same relationship as that of CSTR and PFR. So that's the same. So the same final temperature, 427. All right. So you know how to get that 427? Okay, this is where we obtain the 427 again. That's the 427, okay? The same TX relationship, whether it's a CSTR or PFR, as long as it's adiabatic, we have the same TX relationship. Energy balance will be the same. Energy equation will be the same. So finding the temperature of a CS PFR at 80% conversion is the same. So once you know the temperature, you can now evaluate the K. So K at the initial temperature is known. Okay, cut. And therefore, your K at 80% is determined already. All right. At initial temperature of 298 based on the equation that is given. And also based on the value of K, you can calculate your R for two conversions. All right. So for the two conversions, you calculate your R. And we have the Levenspiel plot. In the Levenspiel plot, similar to that of the numerical or graphical integration. The graphical integration, as you have seen, okay, solving for the volume of the PFR, we have the FAO over negative R sub A. The volume for a PFR is defined that way. So multiply by delta X. Now, this is somewhat numerical integration or graphical integration. You can see that this is your Y, this is your X. Simple two-point rule, parang rectangular integration lang. Okay? Rectangular formula. Area under the curve, which is a square lang. Okay, you just determine that. Simple, as simple as that. So a simple demonstration of numerical integration. Okay, and so two-point rule. Okay, then once you have your RA, you're now ready to define your FA over negative RA and then proceed with the integration, simple integration lang. Take the sum of the areas, average of the area. So since you're given that, FAO is calculated, and so FAO over RA is defined for both conversions. So you get that. And so numerical integration now, two-point rule is just getting the average of the, okay, the simplest rectangular rule. Area here at XO and at X1. Take the average. What's the difference in delta H? All right, so that's a delta H or just simply H. All right, so that is the Y1, Y2. Multiply by X or H gives you the area under that curve. Okay, so the area under that curve, somewhat an average. Divide by 2, again, divide by 2. So you get the average area from X1 to XO. XO to X1. All right, class. So this is that simple formula. Later, you will be using the Simpson's one-third rule, or maybe the Simpson's one-third rule, the five-point rule. Okay, we're in for the Simpson's rule. We reviewed that last time. We divide by 2. So you have 3 points here for the 5-point rule. So this is just the 5-point rule. That is the multiple elemental one-third Simpson's rule, right? How many points do you have now? Yeah, for the Simpsons rule, you have to divide the area into two segments. But then for the multiple, you have to divide each area twice. So that is 1, 2, 3. You now have 4 segments. And for the Simpsons rule, how many points do you have? X1, 2, 3, 4, 5. So that is why you call it the 5-point rule, coming from the Simpsons one-third rule. All right. So that will be for the PFR. So this is a differential equation that you have to solve using numerical technique for if you have a differential, if you have a PFR. Follow, class? This is
Yes.
a somewhat a numerical technique. So ito yung pinaka-basic. So later, hatiin nyo na yung x nyo from several parts para more accurate, of course. All right. How much time do I have? Sa cellphone natin. Okay, we have no more time. All right. So what I need you to study is the self-study na lang yung next lecture, which is just the same. Sorry. So the difference between the PFR and that of the CSTR, if it's liquid phase, mas malaki yung volume, di ba? Pag PFR, pag liquid phase reaction. So that's the difference. For PFR, it's mostly suited for gaseous reaction, and CSTR is mostly suited for liquid reactions. Okay? So also, later you will see. Study as well. Kindly study na lang this lecture. Study the problem. Practice exercise here. And then do the practice na kayo ng calculation on your own. Okay. I-practice na itong non-adiabatic. Ito. This one. Problem exercise 1. Kindly study this problem exercise 1 class. All right. This is for the CSTR and a PFR, which is more complex because you have several parts ng XA. And then, as you can see from here, na-generate natin yung different Y versus X. And so you will be integrating this. This is numerical integration class by taking the sum of the areas, individual areas, yan parang Simpson's rule. This is 5-point rule. Kaya in-explain ko sa inyo kanina yung 5-point rule. Anyway, you can recall that based on your, saan nyo diniscuss to? Advanced math, right? Correct, class? So, i-integrate nyo yan. It's like graphical integration. Okay, getting the area under the curve. Simpson's rule, dalawa lang yung segment. Sa multiple Simpson's rule that we discussed last time, hinati natin sa dalawa. N is equal to 2. Dinivide natin to 2. Ilang elements na yan? Sorry, 5. 5 points. Okay? So, this is the formula. So, you just perform that. And so, you can find naman yung PFR nyo, 317. Based on this is irreversible gaseous. Is this gaseous reactor? Okay. PFR against STR. Let's compare na lang later. So when you compare the results, both PFR, CSTR, 317 sa PFR, sa CSTR ilan? Ang volume. CSTR is asan na yung CSTR natin? 175, ano pa rin so liquid pa ba to? Oh, hindi ko ano. Try niya nga kung liquid siya. Ba't hindi sinabi? So usually liquid kasi. Pag liquid, usually mas mababa yung volume ng CSTR. Irreversible. Should be liquid reaction. Pag kasi mas mataas si PFR, usually siya liquid. 317. So mas mataas pa rin si PFR. So mas ideal yung CSTR ang gamitin sa reaction na to. Okay? So these are just the example. And then you will be working on your problem exercise. All right, so study this one and do the problem set and use your MATLAB again. Work on your MATLAB. Sa MATLAB, meron pa rin tayong toolbox for Simpson's rule. And pwede naman gamitin ibang ano. Pero for this one, sa This one, okay na yung Simpson's rule. Kasi ano lang naman siya, adiabatic. Pag hindi adiabatic, gagamitan na natin ng ODE 45. Alright, class? So that will be all for